Okay. Let us start modeling. It is recommended to start by defining the main components of the model. In our case, the inspection machine and the input queue. Remind that the input queue is the place where the parts wait to be inspected when the machine is busy. To model these components, we go in the library elements. We start from the machine, which is modeled using the instruction resources. Position the mouse on this instruction, drag and drop it into the simulation model. We have now the first element in our simulation model. Click on Resources. A window appears containing the list of resources specified in your simulation model. Obviously, this list now is empty. Click on Add button to introduce the inspection machine as a resource. A window appears, where we can fill all the relevant information for the inspection machine. The number is the identification number of the resource. We input 1. Then we input the name of the machine, simply inspection machine. Obviously, you can choose another name. A lot of additional information can be specified for the resource, such as failures, schedule, costs, states and others. For our system, this is enough. Click on OK. Again OK, and you have finished. The first instruction of the model is done. Now, we define the input queue by adding the instruction queues. You find this instruction in the Elements library. Drag and drop the instruction, click on it and add the input queue by defining the identification number and the name. As the name, we choose inspection queue. By default, the ranking criterion is the first in first out. As in the modeled system. You confirm on OK 2 times, and the queue is defined. After having defined the main elements, we can start defining the model logic. To do this, we move to the Blocks library. No, not this. This library is the right one. Parts arrive into the system from outside. We model parts as entities that arrive into the system with the instruction create. The create block generates entities in the simulation according to some criteria that we easily define. Now, insert a create block into the model, click on it and a window appear. In this window, we define the process of part arrivals. The batch size is the number of entities generated by the block at a time instant. In our system, parts arrive one by one. Thus, we input 1. The first creation is the time at which the arrival process starts. Thus, the first batch of entities will arrive at this time. We keep the default value 0. The interval is the inter-arrival time between consecutive generations. You can input a number, a function or a random distribution. In our case, we input 3 minutes. The maximum number of batches imposes a limit to the number of batches generated during the simulation. By default is infinite. The rest of the fields are not filled in this example. We also add a comment. Remember that a code with comments is useful for a better understanding of the model. In the system that we are modeling, after parts arrive they are moved to the inspection machine. If the machine is busy, parts must wait in the input buffer. We model this with the sequence of instructions queue, seize, delay, and release. Now, we add the queue block into the model. You find it in the block library. Notice that the queue block has automatically been linked with the create block. And then, we add the block seize. Click on Queue, and select the specific line from the list we defined in the element queues. In our case, we can choose only inspection queue. Confirm, and open the seize block. The seize block is used to allow an entity to occupy a resource. In our case, a part occupies the inspection machine. As before, select the resource from the list we defined in the resources element. Confirm, and close. Insert into the model the block delay, followed by the block release. Notice that, this time, the seize and the delay blocks are not connected. Use the connection command to link the two blocks. Open the delay block, and specify the time duration. You can input a number, an expression or a random distribution. The inspection time is 2 minutes and 30 seconds. Confirm, and open the release block. We must release the resource after the part is inspected. In this way, other parts can access to the inspection machine. The model logic is quite intuitive. Parts arrive, wait in a queue, and finally are processed by the inspection machine. After the inspection, parts leave the system. We can say we have built a simulation model of the system. We simulate for understanding the system, not for fun. Therefore, we add something to collect the number of parts inspected during the simulation. To do this, we define a counter in the element counters. Add this block in the simulation model. You find it in the element library. Click it, and add a counter item. We can call it the number of inspected parts. Adding a block from the library elements is like declaring a variable in a general programming language. Therefore, if we don't change the logic, we cannot count the number of inspected parts. To do this, we add a block called counter. We take this from the block library. Position the block exactly where you want to count the entities. The counter increments by 1 each time an entity enters. Open the block, select the counter you defined in the elements, and confirm. Obviously, you can change this by modifying the counter increment. With the block dispose, we represent the parts leaving out of the system. We add some more comments in the code. We save now the file on the disk. Before simulating, it is better to check if the model is correct or not. To do this, click on Check button. The technical details of the simulation experiment are input in the replicate instruction. You find it in the elements library. Add it into the model, open it, and a window with many fields is opened. For this example, we don't need to input all. The replication length is 1 week, or 10,008 minutes. The number of replications is 1. Check again the model. Now, just click the Run button to start the simulation. Open the output file and see the results. The number of parts inspected in the simulated week is 3,360. Or 3,360. Close the file. Stop the simulation experiment. The text is asking us to collect other statistics. Specifically, we have to measure from simulation the Q level, the machine utilization and the system time. For the first two performance measures, we use the element instruction discrete statistics. In this instruction, we specify the variable we want to collect. To collect statistics from the Q level, we use the function nq. The value of this function is the number of parts waiting in the queue during the simulated time. Thus, it is a function of time. We input nq. As for the argument in the brackets, we specify the name of the queue, or the identification number. Then, we specify the name of the statistics. We choose buffer level as the name for this. The statistics on the utilization level of a resource are collected using the function nr. The use of this function is similar to nq. As for the argument, we input the name of the resource, or its ID. This function also depends on simulation time. Its value is the number of resource units occupied, or that are busy, during the simulation. The name chosen for this statistic is machine utilization. These two functions, nq and nr, are Arena functions specific in this software. Now, confirm. Check the model. And run the model. In the output file, we see the two added statistics among the results. For all the statistics, the software provides the estimated average value, the half-length of the confidence interval, the minimum value of the statistics and the maximum value. As for last, the value of the collected variable at the end of the simulation. Other statistics can be calculated ad hoc. The buffer level is always 0 because the inspection time is always smaller than the inter-arrival time. Notice that it is not possible to calculate the confidence interval. This is because of no samples available for this measure. See INSUF between the brackets. The mean utilization is around 83%. The maximum value is obviously 1. The reason is simply that we have only one unit of inspection. At the end of the simulation, the machine is busy. As far as the confidence interval, the software tells us that the samples are correlated. And for this reason, it cannot provide an unbiased estimate. See core inside the brackets. Now, let us go to the last performance measure, the system time. The system time is simply the time a part spends in the system. To collect this time value, we just trace the entity flow. Specifically, we save the entry time and the leave time of parts in some variables. Then, we calculate the system time as the difference between these two values. We use the instruction attributes to save the entry time. The attributes are a kind of local variables at the entity level. Insert the instruction attributes into the model. You find it in the elements library. Open it, and add a new attribute. We call it entry time. Confirm, and close. We know that this is just a definition. Now, we have to save the entry time value in the model logic. We can do this at the create block, or at the queue block. It is the same because there is no time lag between the two events. Open the create block, and search in mark attribute the entry time. Select it, and confirm. The other attributes that you see here are the ones the software saves automatically. After having collected the entry time of each entity, we introduce the instructions tally and tallies. These two blocks help us to calculate statistics. Tallies is an element instruction. Tally is a block instruction. In the element, we define the system time. It is just a declaration. Then, we move to the model logic to insert the tally block. We insert this block after the count block. Connect it to the other adjacent instructions. Open it. Specify the element you defined in tallies. As for the value, we use the function interval. This function gives the result of the difference between the simulation clock and the argument of the function. If we input the entry time as the argument, we are just calculating the system time. Confirm it. Check the model and run again a simulation. Another comment. Now, we use some animation instructions to show the value of the number of parts inspected and the system time during the execution of the simulation. Obviously, the system time is constant and equal to 0.5. You can change colors, add text. We don't explain this stuff, just learn from the software. It should not be too difficult.